Based on fleet-wide statistics we gather from MistAway, at any given time about 3% of the systems with leak detection hardware are displaying error 3, which almost always indicates a leak in the nozzle circuit. In this video, Sizing Up Error 3, we'll talk about how to determine the likely size of a leak in the nozzle circuit and decide whether you should look for the leak or change some controller settings and wait for the leak to get worse and easier to locate. And you can do this while standing at the unit or through the MistAway website. We'll start our discussion with what we know about how the nozzles behave. Remember this chart from the MistAway U videos. We plotted the flow rate for our slimline nozzles across a wide range of pressures. The pumps in our units are set to operate at about 250 psi. You can see that a slimline nozzle operating at that pressure will have a flow rate of 50 milliliters per minute. But not all the nozzles operate at 250 psi because of pressure drop in the nozzle circuit. In MistAway U, we introduced rules to follow during design and installation to help you ensure that each nozzle operates at a minimum pressure of 200 psi. At 200, a slimline nozzle flows at a rate of about 40 milliliters per minute. Now notice something else about this curve. Starting at about 200 psi, the curve flattens out. This means as you continue to add more and more pressure, you get less and less additional flow from a nozzle. You can see by the shape of the curve that in order for the flow rate to get to 60 milliliters per minute for a slimline nozzle, the pump would have to produce about 375 psi, which is literally off the chart. Even if you could adjust the pump pressure to be that high, it would destroy itself pretty quickly. So in a healthy, well-designed nozzle circuit, the average flow rate through the nozzle should be between 40 and 50 milliliters per minute. It really can't be much higher. So remember that flow rate range, 40 to 50 milliliters per minute per nozzle. Now let's quickly review how leak detection works. The Gen 1.3 drum unit with leak detection and the Gen 3 tankless unit both contain a flow meter. Fluid passing through a pinwheel in the meter causes it to turn. Magnets on the outside perimeter create electronic signals that are counted by the controller and then turned into an estimation of the flow. After each mist cycle, the controller in the unit reads the actual flow that went through the flow meter and divides it by the nozzle count that is programmed into the controller. This is the AFR value that you can see in the data menu or in MistAway. The controller then retrieves two values from its settings. The first is the NFR, the nozzle flow rate, which is the predicted or target flow rate per nozzle. It defaults to a value of 40, but you can change it in the data menu. The controller then retrieves the tolerance, TOL, in the data menu, which is a factor that makes the system more or less tolerant of leaks. This value is expressed as a percentage of the NFR, and it defaults to 25, 50, or 75%, depending on the nozzle count in the controller. We'll talk later about why and when you might want to adjust it. If the AFR is less than the NFR plus the tolerance, the controller thinks the system is okay. If the AFR is greater than the NFR plus the tolerance, the controller enunciates error 3, indicating a leak. Here's an example. The NFR has the default value of 40 milliliters per minute per nozzle, and the tolerance is 50%. Multiplying 50% by 40 means the tolerance is 20 milliliters per minute per nozzle. And adding that to the NFR of 40 means that the controller will enunciate an error 3 if the AFR is greater than 60 milliliters per minute. So does this mean if you encounter a unit with an error 3 and check the AFR and you see 75 milliliters per minute that you've got a large, very obvious, easy to find leak? Not necessarily. Here's why. Let's visualize what's going on in a nozzle circuit with a leak during a mist cycle. During misting, the system is in steady state with the lines full and pressure constant. Even the flow rate through the leak is at a constant flow rate. At the end of the mist cycle, the controller stops the pump and holds the agitation valve open. You'll see the word hold and a countdown in the display. The pressure in the nozzle circuit drops very quickly as a small amount of fluid flows back into the unit through the auto drain valve. When the pressure drops, the check valves in the nozzles close and they stop misting. As long as the agitation valve remains open, fluid will drain back into the misting unit. It will also drain through the leak. Next, the controller allows the agitation valve to close. This stops the flow back into the unit. But the lines continue to drain out through the leak. It is almost inevitable in this situation that some, maybe a little, and maybe a lot of the fluid can leak out between mist cycles. How much leaks out depends on the configuration of the nozzle circuit, the size of the hole, and the time that passes until the next mist. When this system executes the next mist cycle, the controller opens the agitation valve and the pump starts. The pump has to completely fill up the lines before the pressure increases, and the check valves in the nozzles can open and allow them to mist. The system then returns to steady state just as we started. So what will the flow meter reading be at the end of this mist cycle? You can think of it as having three components. First, there's the normal flow through the nozzles, which we know to be 40 to 50 milliliters per minute per nozzle, and not much more than that. Second, there's the flow through the leak itself, which can be either large or small or in between. A pinhole caused by a squirrel might be small, while a large leak might be caused by the tubing having pulled out of a fitting. Third, there is the amount of line fill that leaked out of the nozzle circuit between mist cycles. This could also be either a lot or a little, depending on where the leak is in the nozzle circuit and how gravity affects it. So how do we use this knowledge? To determine the actual size of the leak in the nozzle circuit, you need to measure the flow rate starting with full lines. When we do that, we eliminate the line fill component of the AFR. Since we know the normal flow through the nozzles, by difference, this allows us to tell whether the leak itself is large or small. First, note the AFR in the data menu from the cycle that threw the error 3, then clear the error from the controller. Next, run an inspect cycle for 30 to 45 seconds to make sure the lines are full. Then immediately after you stop the inspect cycle, run a remote or manual mist to completion. Now look at the AFR in the data menu. This value should definitely be smaller than the one you noted earlier, since the new AFR excludes the volume required to fill the lines but includes the flow through the leak. As a rule of thumb, if the AFR starting with full lines is 60 milliliters per minute or higher, the leak is pretty large and should be relatively findable. For example, an AFR of 60 would mean the size of the actual leak is equal to the normal flow of 10 to 20 nozzles misting. If the AFR is in the 40 to 50 zone, the leak is probably small and may be difficult to find, especially if it's buried in a riser line. In this case, rather than looking for the small leak, we recommend increasing how tolerant the system is to leaks, and then letting it operate until the leak gets much larger and easier to locate. You do this by increasing the tolerance, TOL, in the data menu to 100%. Of course, you can do all this through the controller if you are on site, but you can also do it from the MistAway website, where you can run inspect, run a mist to get the AFR with full lines, and reset the tolerance if the situation calls for it. All you'll need is clearance from your customer to mist their system. That's all for this video. We plan to release another related short one about calibrating your system so that you get more accurate flow rates and leak detection soon. So stay tuned.